Thank you, and can everyone hear my voice on the mic? Okay, it sounds clear. So I do apologize that I sound a little low and gravelly like Frank Sinatra. I caught a nasty cold yesterday. Sounds a bit like this. If you have trouble hearing me, just sound out. I'll repeat. Okay, so thank you very much for the warm welcome. I'm Qirong. I'm here to talk about how we in the AI and ML industry do distributed, fast, high efficiency machine learning, artificial intelligence programs at scale. Before I begin, I want to say a bit about where I come from and what company I work for. We are a very recently funded startup out of Pittsburgh in USA. That's where Carnegie Mellon University is. We have about 15 employees, growing to about 30 within 6 months. Founded in June this year, got funded in about and kind of the end of September, early October period. Uh, Originally, we are an academic group that specialized in, leading edge research for how to do these programs at scale, how to do them very fast, very efficiently, while still being correct. And we decided that we wanted to take this technology and commercialize it, make it into a development platform for AI and ML. And so that's what we're doing, building an enterprise AI and ML development platform. And we have focus in, of course, artificial intelligence and machine learning, but also distributed systems, database systems, human-computer interaction. We're a pretty diverse company. And today, what I really want to talk about is explaining how we get our artificial intelligence and machine learning programs to run at extremely large scales. And to understand what that really means, I want to talk about four needs for these programs. One, you should be resource efficient. What that means is that you should use as little CPU, GPU, network, memory resources as possible, right? You want to get it to be as efficient as a really highly optimized program that's running on your laptop. At the same time, you want it to, of course, scale with increasing problem size, with increasing hardware. You want to get linear, near ideal performance scaling with more hardware. You, of course, want it to be correct, and you want it to be general purpose. Artificial intelligence and machine learning is a very, very diverse field. Deep learning, it's popular. It's only 10% in the field. There's plenty of other programs out there. And in the current landscape, I think we can divide it into systems that are definitely perfectly, exactly correct, very good at doing it, as well as very general purpose. There's any type of program, not just AI, not just ML, database programs, SQL queries, you name it, they can run on this. And then from the AI and ML industry, you have platforms that are going to be really efficient. They're very resource efficient. They're correct. They usually specialize for one or two forms of AI and ML. They don't cover the whole space. And of course, naturally, they don't cover things like SQL programs, database programs, the general big data programs. So I want to define where our company operates in and what our focus is on. It's basically systems that are efficient, scalable, correct, and general in the context of all AI and ML programs, but not necessarily in the whole context of big data, because that's a separate type of technical discussion. Right. And by focusing specifically on AI and ML programs, what I want to show you today is that it's possible to get multiple order of magnitude speedups just by being very careful and very introspective about what you do on these things. Right. So I want to give an example. This is probably a familiar example to a lot of people that are practitioners of AI and ML. It was an example that I ran into myself years ago when I was doing an industry internship. You want to take an AI and ML program, you want to scale up from a workstation to a production cluster. You created a prototype on your laptop. It's really fast, it's really optimized. Let's say you can do 1 million users, 1 million events in about 6 minutes. Okay, maybe the first try, you use Hadoop to do it. You want to run it in real time. So, okay, I want to do it on 100 million users, 100 million events. That's 100 times problems. I've got a very large cluster, 1,000 machines. So shouldn't I be able to do this in about 0.6 of a minute, less than a minute? What usually happens for AI and ML programs run in this way is that it can take over a week to finish. And that may seem quite surprising to you, but let me explain why. For a typical Hadoop execution, what happens is that you've got multiple machines. They're running the AI and ML program. They'll do some computation. Because machine learning and artificial intelligence programs are what we call iterative, you're going to barrier basically. You're going to have a barrier here to stop, to talk, to exchange parameters. Parameters are the numbers, the values that make up a machine learning program. You'll do this again, you stop and talk. Sooner or later, you get a situation that looks something like this. In a general large data center, large cluster, you'll have one or more machines that's going to be a lot slower than the others. There's many causes for this. Sometimes it's temperature fluctuations in the data center. Sometimes it's the fact that someone else is using your cluster. Sometimes it's the fact that your I/O bottlenecked on disk or memory on one particular machine. But because of this need to wait for all machines to stop and talk, there's always going to be at least one very slow machine holding up progress. And why do I think that this is going to become a more severe problem in the future? Well, the current trend in artificial intelligence and machine learning is that very large models are good for very large data. The bigger your data, the more parameters you want to extract more intelligence to fit it better. For example, in text extraction models, for example, topic modeling, 1 billion to 1 trillion parameters is now norm. And deep learning, generally, they're in the hundreds of millions to billions of parameters. Recommender systems are generally in the 10 to 100 million range these days. The point is that all of today's model sizes are gigabytes. Right, they're gigabytes. This is not trivial to exchange over a network when your typical bandwidth over, say, Amazon EC2 is maybe 100 megabytes per second. Right, you're talking about many tens of seconds just to exchange a complete copy of the model across the network. And the fact is you have to do this. AI and ML programs benefit from frequent synchronization between iterations. Efficiency, correctness depends critically upon this kind of frequent synchronization. And in case of Hadoop and Spark, you essentially use joins. For example, Spark's RDD join to synchronize. The parameter shuffle that's caused by this generally takes about 90% of the execution time due to the size of the model. And I'll probably be showing some benchmarks later to show kind of how this manifests. So what I'm going to do in this talk today is to re-examine how parameters are stored and synchronized between multiple machines in a data center scenario. Right, and hopefully from this talk you gain a bit of understanding of what researchers and industrialists in AI and ML do to speed up their programs. So a bit of basics. There's essentially two ways you can exchange the machine learning model parameters. Again, you can think of this as the brain, the knowledge of an ML program. There's two ways you can store and sync them across multiple machines. One is to adopt a centralized storage mechanism where there's a single server. It sends entire copies of the parameter, I call that W in this slide, to the workers, and the workers send changes in that, delta W back. And there's a decentralized peer-to-peer paradigm, where you're sending changes delta W to back and forth in workers. I'm bringing this up now because it turns out you have to use both of these together to design a really efficient system. They're useful in very different situations with very different cost-benefit trade-offs. Now, let's talk about centralized storage. And I first want to introduce the bulk synchronous parallel paradigm, which is actually the keystone, the science that underpins systems like Hadoop and Spark. It was invented many tens of decades ago, by a computer scientist named Leslie Valiant. It's been extremely popular since then because it really allows you to program distributed multi-machine programs very easily, but correctly. It's always guaranteed to be correct, right? Why is it correct? If you take a look at a typical machine learning computation, you split the data, you do computation of updates on a local shard of data. That's the little black arrows over there. You then aggregate. That's the barrier, the little light blue colored bar over there. Right. That alternation of computation and synchronization, that synchronization is called a barrier in bulk synchronous parallel. It's guaranteed to produce the same result as a workstation or laptop. And the key property here, a bit of science, is that it's called serializable. The serializable property ensures that it's equivalent to running it on your laptop, on a workstation. Now, the trouble with BSP, when you have a lot of barriers, is that there's no ideal distributed system. Networks are very slow. Your typical network connection is 1 gigabit. That's about 100 megabytes per second, but I just said that machine learning models are starting to go into the gigabytes. Machines can be running out of jobs. Users can be running out of jobs. That creates resource I/O bottlenecks. So BSP barriers are very slow in a large data center. And in fact, what you find that for a typical machine learning program on 32 machines, program in, say, even a high-performance computing BSP-style system, you're going to find that 90% of your CPU resources are actually wasted waiting for these BSP barriers. What that means is that if you throw 100 machines at a problem, you're getting the performance of 10 machines, right? It's not very efficient at all. So there's another extreme, I think, comparison point to BSP, which is what's called completely asynchronous learning. This is something that's taken off in the machine learning and AI community a little while back, where you're just going to say, I'm going to completely throw out my correctness guarantee out the window because machine learning programs are always approximation programs. I'm going to take a risk. I'm going to allow the workers to go ahead and compute without talking to each other. That's illustrated by the asynchronous diagram in the bottom right. This is pretty common in machine learning. So you've got this dichotomy between safe and slow, fast and risky. And it's kind of hard to say, look, do I want to be safe but very slow? Do I want to be fast but risk the result coming up wrong? There's actually, a middle ground, which is what I'm going to call partial synchronicity. You clearly want to mix interleave for efficiency. You want to pipeline your network communications with computation. You want to let workers go ahead when they can instead of waiting, but not too far. You also need a form of what I call straggler tolerance. That's to say, slow machines. You want them to catch up somehow. You don't want them to slow down the program forever. And I'm going to introduce to you a model of computing that's an evolution of bulk synchronous parallel. It's called the cell synchronous parallel programming model, bridging model, that it simply says the fastest and slowest workers are going to stay within S steps, S iterations of each other. It's fast like asynchronous because workers have the flexibility to deal with resource fluctuations in the cluster, but it's correct like bulk synchronous parallel, and that may be a little surprising, but there's a mathematical proof that shows that SSP is in fact close to serializable. For a machine learning program, this is actually good enough. Okay. A second thing that one needs to do to ensure that centralized systems can perform well is you need to perform some form of managed network communication because, again, these models are very large, gigabytes. They take 10 seconds, 1 minute to transfer over the network. You need to be very careful about how you handle that. So an SSP allows you to have the workers go at their own pace, but you still want to spread that communication all across the computation. You want to be having the network talking all the time, even as you compute. You also want to prioritize updates so that you get high network efficiency. And we can show that all of this built together has the same mathematical properties as a SSP system, as a BSP system. It's guaranteed to be correct for AI and ML programs. Right. All that leads to an architecture that we call Petuum boson. This is a stale synchronous parallel plus managed communications parameter server. Parameter server is simply a type of key value store, type of distributed shared memory that partitions the model across a bunch of machines, it shards it across a bunch of machines, and it serves workers that are sending changes delta W to the servers and drawing the full model W from them. Okay. In our benchmarks, this is about 200 times faster than Spark. For a collaborative filtering task such as matrix factorization, we're talking, say, 32 machines, about 250 million parameters. So we're talking about 1 gigabyte parameters here, and about 1.3 gigabytes of data. This actually turns out to be the maximum setting that you can run with Spark on 32 machines with 32 gigs of RAM each. Any larger, and it will run out of memory. But I mentioned at the start of the talk that resource efficiency is really important for these AI and ML systems because the models are growing very large. And our system can handle about 256 times the data and about 16 times the parameter on up to 128 machines. More importantly, not only are we resource efficient, that's the left graph, we're also scalable. Scalable in the sense that if I throw 32 machines at it, I'm getting about a 25 times speed up. So it's about nearly ideal. It's something like 95% efficiency for every doubling of machines. In contrast, high performance computing systems and say bulk synchronous parallel dependent systems such as Spark do not scale well with machine learning programs. And again, this has to do with the limitations of the BSP model when faced with very large model parameters and very limited network resources on the data center. So that brings me to the end of the first part of my talk. That's how to speed up centralized systems. I'm going to talk about how to speed up decentralized peer-to-peer systems now. And to do this, I'm going to focus on a particular class of AI and ML models that I'm going to call matrix parameterized models. This includes deep learning, topic modeling, multi-class logistic regression, distance metric learning, sparse coding, group lasso. It covers almost every AI and ML model that has a matrix parameter, especially relevant to deep learning, as we'll see in a bit. So, in fact, I already said that machine learning models are in the gigabytes. For matrix parameterized models, the growth rate is even faster because you're not talking about a vector of parameters anymore. You're talking about a matrix. There's two ways for these things to grow. And oftentimes, they're going to grow in the density of the data. That's the number of feature dimensions for an AI and ML program. It's going to grow in the number of classes for object recognition. It's going to grow the size of your dictionary, the representation, the quality of your model. So these things are not just in the ones of gigabytes. They usually go up into the tens or hundreds of gigabytes. It's extremely costly network synchronization. But there's something you can do about it. By looking at the mathematics of AI and ML programs, you'll find that the update matrices delta W are actually equal to some function on two small vectors u and v, what we call a mathematical Alta product. So, by applying a bit of smartness to this, you don't transfer delta W across the network. You transfer u and v across the network. You reconstruct delta W at the receiver. That gives rise to a system we call paramobvious, which is what we call peer-to-peer sufficient factor broadcast system. It's fully peer-to-peer. Machines broadcast the changes u and v, and they're used to reconstruct delta W on the machines. Right? This is a lot more efficient, a lot cheaper than setting the matrix delta W itself. And you can go a little further. This is kind of the crux of my talk. You can hybridize both systems, Boson, which is the centralized system, Orpheus, which is the decentralized system, to do a parameter server plus sufficient factor broadcasting hybrid system. And this is going to be really useful for problems that have a mix of large and small matrices or vectors, really. So for the small matrices, you want to synchronize them frequently using a master-slave parameter server architecture. For the large matrices, you're going to do it in a peer-to-peer fashion using sufficient factor broadcasting. So it's really two communications topologies in one system. And it's a very good reason why we want to do this. So if we take a look at a typical deep learning model for image recognition, object recognition, a convolutional neural network has densely connected layers at the end of the model. This is a pretty old example, but still relevant today. You're talking about matrices that are something like 496 by 496, so that's about 17 million parameters there. For these, you're going to decompose using SFP into the UV vectors, transmit it across, reconstruct the destination machine. But the earlier layers, the convolutional layers, these are very small matrices, 11 by 11. They're not even a kilobyte in size. You synchronize them using a parameter server topology instead because that turns out to be a lot more efficient when implemented in practice. So what does that give us actually? Well, it gives us Petuum Poseidon, which is our deep learning in-house system, which does it really fast, compared to distributed TensorFlow and distributed Caffe, which are considered pretty state-of-the-art. We're about 10 to 20 times faster than them. And this system also supports programming in the TensorFlow language, in the Keras language, in the Caffe language. We do all of that by basically being very careful about our network and computational engines, right? This gets you almost ideal scaling. So this is actually a network called VGG19. It was one of the competition winners, I think 1 or 2 years ago. We're running these on state-of-the-art hardware, 16 machines, Titan X NVIDIA graphics cards, about 14 million images, 22,000 image categories. What you find is that this might be a little hard to see from the graph, but there's this yellow and blue line over here. That's the Poseidon system. Blue line is ideal scaling. Orange line is the Poseidon system. What we're showing is that we are almost perfect. This is something like 95%, 97% efficiency within every doubling of machines. In contrast, TensorFlow at some point basically chokes. For a model of this size, it cannot handle it, and additional machines actually cause it to slow down. For Caffe, the story is a little better. I know there's some implementations on Caffe and Spark by Yahoo Labs. There's also one released by the Berkeley Amp Lab. We get something like maybe 3.3 to 3.5x increase in speed with 16 machines. But that's far from ideal. And again, what we see is that Poseidon gets nearly ideal. That's the orange line versus the blue line over here. Okay. So having talked a bit about that, I want to stop for a second and demonstrate some aspects of our system, because earlier I talked a lot about resource efficiency, I talked a lot about scalability, but I really want to show you that it's also correct, general purpose, programmable. So that's kind of hard to convey via PowerPoint presentation. So I'm going to break a little bit here and switch to my console. Okay. So what I'm going to show here is an example of a Petuum machine learning program. The core code is about 30 lines of code to write a simple logistic regression that's between lines 15 to 46 over here. This is a completely self-contained logistic regression distributed cluster application on Petuum OS, which is our lead product that does data center computation. Now, I'm going to show you that this runs. First, I'm going to demonstrate it on my laptop. Petuum OS runs on both laptop, runs on data center. Okay, so I'm going to do a Petuum OS run. This file is called petuum.lr.py. I apologize for the font size. And I'm going to do it on a dataset that's small enough to run on my own machine here. Okay, so after a little bit of loading, okay, it's running. It's getting a certain accuracy. And it finished about 8 seconds. Now, I want to show that this is programmable. So I'm going to do a little trick here to greatly improve the accuracy. For those of you that are educated in artificial intelligence and machine learning, you'll know that there's something called regularization. It's a technique that's applied to machine learning models. I'm going to show you that I can do it right on the spot here. So I'm going to do a weight of 0.5 times the second derivative times the first derivative of a L2 norm on the parameters, and that's basically technical speak for L2 regularization. I'm going to run that again. Right. And what you see now is that the loss function, as it ended at about 800, you can tell regularization is working because it goes all the way down to like 0.6, and accuracy jumped all the way to 100. So that's all and good. Now I'm going to do a demonstration. I'm going to delete this line. I'm going to do a demonstration for a larger data set on Amazon EC2. So first, I want to show that I've got about 16 instances running here on EC2. And what I'm going to do is I'm going to launch a Petuum program on all of them. So to do this, I'm first going to deploy my Petuum LR program onto AWS. Okay, now I'm going to do a side-by-side comparison on a larger data set. So the left is my laptop. The right is going to be my AWS cluster. Right, it's going to be a data set that's about 1.5 orders magnitude larger than the one. So okay, I'm going to start the one on my laptop first. I'm going to start the one on the cluster. It's going to take about 10 seconds to load the data, and we'll see what happens. So you can see the cluster version on 16 AWS instances has already started. In fact, it's already finished. My laptop's still loading the data, unfortunately, because it's that much. Okay, so it's just started. So you're going to see that this is really, really slow compared to a cluster. And just to prove to you that this is in fact running live, I'm going to take this file again. I'm going to put in the L2 regularization I talked about. So grad plus equal, I'm going to do a weight of 0.5 times 2 times the value of the weight vector for logistic regression. I'm going to do a redeploy on my cluster. I'm going to relaunch. So pay attention to the loss function, pay attention to the accuracy. You'll see a dramatic change once I redeploy this. It's going to take it's about 20 seconds to load the data in this case. Okay, so you can see now the loss is dropping very quickly to less than 1, and the accuracy goes to 100 straight away. So what I've demonstrated here is that Petuum OS, which is our system, our product for programming general-purpose AI and ML programs, it's got a Python interface that's very natural to write programs in. You write this on your single machine, you test this, you deploy this on your laptop, you deploy this on the data center whenever you want. You can push the changes live immediately and run. And this is only, in fact, the command line interface. We're still developing our graphical user interface, which I think we're going to be releasing this sometime in the first half of 2017. Right. So my laptop's still running that large data set from there, so I'm just going to ignore that and go back to my talk. All right. Okay. So the talk today, while I spoke about how to make centralized and decentralized storage go very, very fast on data centers. That is, I think, part of the work that we've been doing. In general, we look at many scientific aspects of AI and ML computing. For example, I talked about the bridging model, BSP to SSP today. There's some stuff I didn't talk about today, but it's part of the work that we put into our Petuum product that includes resource scheduling and load balancing to make these programs go even faster. And work on programming interfaces and work on a lot of load balancing and scheduling creates even more order of magnitude performance increases. There's another topic I actually want to touch a bit on because it's pretty relevant in today's society. There's sometimes a bit of confusion behind what people call an artificial intelligence or machine learning program. There's a lot of talk these days about general AI. I want to say that we're nowhere near there, and this is coming from me. I'm an AI and ML researcher. In AI and ML, what's actually used today to power all the applications, including deep learning? These are mathematical programs with a single clear and quantitative function. They have a very explicit mathematical model, very well-established theory and practice. It's very familiar to people in applied statistics, people in applied mathematics, even people in physics will understand these models. Hardware is always electronic devices. Software is always built out of algorithms such as search, optimization, stochastic models. They have their advantages, they have their disadvantages. This is kind of like building an advanced fighter jet. You put pieces together, it's very careful engineering. Human intelligence, on the other hand, which people sometimes conflate with general AI, this is not well understood. The biologists say this is not well understood. I was actually a biologist before I became a computer scientist, so I know this. It's multiple, fuzzy, difficult to measure functions. It's got an unknown mathematical model. It perhaps has unlimited potential, far more than what we think. Hardware is living organisms. Software, I can only say that the current models, especially those promoted by computer scientists, are grossly oversimplified. You can't engineer a bird, is my point. You can engineer a jet fighter, you can't engineer a bird. What we're aiming to do in Petuum is actually repeatable, standardized engineering for artificial intelligence and machine learning. We want this to have repeatable building blocks. We want an engineer to be able to take pieces of an AI and ML program, assemble them together, and always get the same result every single time. No guesswork involved. Right? There's no mystery to it. In today's talk, I spoke about data center, artificial intelligence, and machine learning for a variety of that blue layers AI and ML algorithms, families of algorithms. There's literally like 10 plus families and maybe hundreds of distinct algorithms that are all in that layer. What I've been concentrating on today is data center and cluster work on Intel CPUs, NVIDIA GPUs, Ethernet, maybe InfiniBand as well. But our long-term vision for our product is really standardization across a large swath of the AI and ML space, from the verticals to support the range of verticals that people care about. And again, here I'm talking about very precisely defined tasks, not general AI, right? We want to do this on a variety of compute scenarios, workstations, data centers, mobile, eventually embedded in IoT and manufacturing equipment. We want to do this across a range of hardware, at least some of the more promising ones, such as FPGAs and eventually wireless and 4G. But most importantly, we want to do this repeatably. We want to do this in a scalable, correct, efficient, and general way. And I'm going to end here by talking a little bit about the products that we're going to launch in the future. This is all coming in the first half of 2017. So we have 3 product lines for the moment. One is called Petuum OS. What I showed you was a very, very, very early alpha of it. It's going to create, deploy, manage data center AI and ML. It's going to be about 100 times faster than Spark for these programs. It's going to allow you to write them in Python, C++, and a few more languages that we will support soon. But we anticipate most of our users will probably be using Python for this. We also have Petuum Poseidon, which is actually going to launch, go into beta a little earlier. That's around the March timeframe in 2017. It's multi-node deep learning, about 20 times faster than TensorFlow, scales from 1 to 50 plus GPU-equipped machines. So you no longer have to get a machine with 8 GPUs in it. You can instead run 50 machines with 1 GPU each, and you'll still get really good performance out of it. As good as 1 machine with 8 GPUs, well, I can do 8 machines with 1 GPU each, and that's sometimes a lot cheaper. We allow you to write deep learning with Caffe, TensorFlow, Keras interfaces. And I also want to say that in the vertical domain, we are looking into some medical applications, such as involving electronic health records and medical imaging. Kind of mentioning all of this because our Pittsburgh office is actually still recruiting very actively. We're 15 people now. We want to grow out to about 30 people within actually 6 months. And we think this is going to be a very, very exciting journey, and we're actively looking for people to come join us on this. With that, that'll be the end of my talk, and I'll take questions.
If anybody has any questions, I'll pass the mic. I guess I have a question. What's the commercial, is it a commercial product sold to institutions or open source, or how do you work with it?
We will have a mixed model. There's very likely to have a open source component to attract developers. For commercial grade operation on large data centers, we will be doing this in a licensing based model. Our target is really enterprise AI and ML development and some measure of scientific academic AI and ML development as well. But we also want people to be able to try to do this on a single laptop. And we're actually running a trial pilot program at CMU very soon, where we're actually introducing this into some of the deep learning and machine learning classes.
Any questions?
Yeah, so you mentioned that you specifically excluded big data analytics from this particular talk. Wondering what's the difference that you see here in terms of, what does your product offer in that regard?
So that's a very good question. The reason why I did not talk about big data analytics is because there's a trade-off between how general purpose your system can be and how efficiently it performs for a specific type of task. Now, big data analytics includes, especially the most popular, I believe, is SQL queries. Those are a very different type of program from the iterative, convergent artificial intelligence machine learning world. They require a vastly different set of optimizations, and many of the optimizations that you do for AI and ML programs don't work for SQL queries. Right. So that's a distinction that it's worth explaining a little bit now, that AI and ML programs, a lot of times, close enough is good enough. For a SQL query, you're either right or you're wrong. There's no close, there's just right or wrong. Right. So the big data analytics, I think we foresee ourselves having some form of integration with the Spark world, having some form of integration with the other big data environment. Right. We're not there to replace it because I think that's frankly not what this technology is for. This technology is very specifically to solve many of the efficiency and affordability, the capital expenditure, operational expenditure challenges you find in AI and ML. Capital expenditure in the sense that we want to get that resource usage down to 100 of its size. Operational in that we need to make this a lot more general, a lot easier to program. Right now, what you have is a picture of scattered tools for AI and ML that you kind of pick, assemble a team of engineers and scientists, crank out one program, and the next time you've got another application, you start that over again. We want that to be a lot more repeatable, a lot more standardized.
Yeah, and it seems to me that your system is focused on addressing the size of the models. What functionality deals with the size of the data sets, especially around, say, deep learning?
So for size of data sets, this was not the subject of my talk, but it's a good question. We are developing our own data management system, which is going to be very much focused on both large offline sets as well as streaming data. At this moment, all I can say is that it's going to be very much an in-memory system that I think has analogies to what Aluk Show does for the big data world.
All right, thank you.
You showed one of the slides that had, I don't know what the matrix was that you were discussing, but it was a W matrix. And then you talked about instead of shipping the W matrix, you split it up into its components. Can you just speak about a little bit more about how breaking that W matrix into its components actually is building efficiency into the system?
Mm-hmm. So the first thing you need to know is that it's actually correct. If you take a deep learning, for example, deep learning, but it's not limited to just deep learning. Take a deep learning program, calculate, if you look at the backpropagation algorithm, the matrix turns out to be a outer product of two vectors. An outer product is basically a function that takes two vectors and spits out a matrix. It's a very exact function. It's totally deterministic. What we're doing is that we're shipping the vectors across the network first, and then reconstructing the matrix at the other end. And this is important because the matrix could be megabytes or gigabytes in size. And deep learning, in a typical deep learning scenario, we are talking about every GPU processing tens or hundreds of images per second. So the amount of communication across the network incurred by a single GPU is measured in the hundreds of megabytes, sometimes gigabytes per second. If by taking a large matrix and breaking it into two vectors, and by the way, I should clarify, the vectors have dimensions equal to the length and height of the matrix respectively. So we're taking what is an n times m matrix and dropping it down to n plus m size. This completely discounts the amount of talking you need to do over the network. And that's basically building efficiency into the system. However, there's also, it's actually not as trivial as my talk might suggest, because you have to deal with certain issues that arise in a much larger cluster. And we actually have technologies such as what we call partial broadcasting, where we only broadcast the vectors to some machines and let the results propagate along over the other machines over time. Right. So there's a number of trade-offs involved in here, but the short story that I'm presenting today is that this is actually a very important technique. It's a technique that's absent in many other distributed deep learning systems, and that's how we're able to gain an order of magnitude more performance over them.
Any other questions? One more for me is, are you doing any graph-based analytics?
Graph-based analytics. So this is not something that we are immediately considering. A lot of graph-based analytics actually falls more into the what I'm calling the traditional computing or database paradigm, in that exactness is important, close enough is not good enough. It is true that graph-based systems have been used to program artificial intelligence and machine learning programs. GraphLab was a famous example. Prego is another famous example. But graph systems are actually more general than AI and ML, and so we don't pitch it that way.